So now we're switching gears again, and we're going to talk about acid-base properties of salt solutions. I think there's a misconception that salts are neutral. Well, table salt, NaCl, is neutral, and it has certain characteristics because of the acid and base that they're related to that makes them neutral. So we've seen though that many ions can act like acids or bases. And so a lot of times if they're in solution, we have to take that into consideration. So for example, this salt, NaCN, sodium cyanide, when you dissolve it in water, it breaks apart to give Na plus and Cn negative. So now, as you'll come to see, sodium we can ignore. Sodium comes from one of those strong bases, so it's really not going to interact with water at all. However, Cn negative is the conjugate base of a weak acid, HCN. And so it's going to have some acid-base properties with water that we have to consider. So if you actually have a 0.1 molar solution of this NaCN, it's very basic. It has a pH of 11. So again, it's because of this Cn ion that can act like a base in water and can remove the hydrogen and creating more hydroxide ion. So here's what I was saying. So yeah, the sodium is unreactive with water. And like I said, in just a minute, I'll tell you how you can know that. But we can't ignore the conjugate of a weak acid. And so when it's in water, it will react to form some HCN and OH negative. And so this is why the solution is negative. Even though originally we're talking about a salt, because the conjugate, the negative ion of the salt is a conjugate base, it will act in a basic solution, in a way that's basic. I just said that. And I just said that too. So OH negative is the product, and so that's why it's basic. So it's the hydrolysis of Cn negative. So it's really just like saying, okay, Cn negative is a weak base, and so we need to consider the hydrolysis of Cn negative. So it's really not super complicated, but we have to add a few more little complications to the matter, so it does become, like I said, it does become more complicated, even though it's really doing the same thing. All right, so the hydrolysis of an ion then is just the reaction of that ion with water to produce the conjugate acid and hydroxide, or the conjugate base and hydronium. So like we said here, the hydrolyzation of Cn negative gives us OH negative and the conjugate acid. And it's a base ionization, so we can have a Kb expression for it. In a similar way, NH4 plus is acidic, and so if you added a salt, for example, if you added NH4Cl, which is a salt, the NH4 ion will also hydrolyze, but it's because it's an acid, it will hydrolyze to give us H3O+. So we can use the Ka expression for that. So we could write the Ka expression. All right, so before we get into that, how can you predict whether a salt will be acidic, basic, or neutral? All right, so it all goes back again to those 6 strong acids and 6 strong bases. Let me erase that and try again. I'm going to put my 6 strong acids over here, just to review. Right, we have HCl, HBr, HI, HNO3, HClO4, and H2SO4. And then we have our 6 strong bases. Told you it's going to be important to know those. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. I always get confused. Magnesium is not one of them. So I kind of go, you start with lithium, sodium, potassium, and then go over to the right of potassium is calcium. So calcium, strontium, barium. All right, so what we want to do is remember our 6 strong acids. They completely dissociate. And because they're so strong, their conjugate acids are their conjugate bases are very, very weak. If HCl is really good at giving away an H+, Cl negative is really bad at accepting it back. And so for all intents and purposes, these 6 negative ions, and the negative ion here would be HSO4 negative, these 6 negative ions never interact with water. They're pretty much neutral. And in the same way, these 6 positive ions, and I know it's a little bit hard to imagine by the way we're talking, but these 6 bases dissolve so completely that they don't want the OHs back. And so these 6 positive ions will always be neutral when they're in water. So it's anything else that's not one of these 6 negative ions or 6 positive ions that we have to consider. All right, so again, just saying what I just said. Anions of weak acids are very good proton acceptors. So if you've got a weak acid, they're really good at accepting the hydrogen back. But if they're strong acid, they're not. So any anion of a weak acid are considered basic. So like I said, anything that's not Cl negative, Br negative, I negative, NO3 negative, ClO4 negative, or HSO4 negative, anything else will sort of be basic. So Cn negative is an example of this because it's HCN is not one of the 6 strong acids. The Cn negative ion is basic. And then the anions of strong acids, therefore, have no basic character. In other words, you can ignore them. So those are our 6 negative ions, Cl, I, Br, NO3 negative, ClO4 negative, and HSO4 negative. So any of those 6 in water have no reaction, and so basically we can ignore them. So then, like I said, the cations of weak bases then are acidic. So NH4 plus is an example. So any positive ion, and let's just write them up here again. Lithium, sodium, potassium, calcium, strontium, or barium. These ions are neutral in water. Any other positive ion will be acidic. So we have to consider any other positive ion that's in solution. If it's one of these 6, we can ignore them. So then you have to examine both ions. So let's look at this one. This is potassium acetate. So we consider the potassium, and we know potassium is one of those 6 strong, comes from one of the 6 strong bases, so we can ignore it. Acetate, however, comes from acetic acid, and because it comes from a weak acid, it itself is basic. So the K is neutral, and the acetate is basic. So this salt will be basic. Right, the K plus we can ignore. However, the acetate ion, because it comes from a weak acid, it itself is basic. It will react with water to give us the conjugate acid and OH negative. So it's basic. So a solution of potassium acetate will be basic. So I think we'll do a few more examples in a second. So if you have a salt that the positive ion, the positive ion comes from a strong base and the negative ion comes from a strong ion, then it's neutral. Comes from the positive ion. That's what I should do, positive ion, positive ion. Then neither of them are hydrolyzable, it's neutral. What's our example of that? NaCl. Na comes from one of the 6 strong bases, Cl comes from one of the 6 strong acids, and it's going to be neutral in water, and neither one is hydrolyzable. Both are so weak that neither of them react with water. However, if we have the positive ion comes from a strong base, but the negative ion comes from a weak acid, then it's going to be basic. Basic solution because the conjugate base is hydrolyzable. What's an example of that? NaCN, or what was the other one? Potassium acetate, KC2H3O2, if the negative ion. So clearly, if you have the positive ion comes from a weak base, so it's not one of those 6, and the negative ion is one of the 6 strong acids, negative charge, then it's going to be acidic because the positive ion is going to be hydrolyzable. So an example of that, NH4 is a positive ion that's not one of the 6 positive ions. And then Cl negative, though, we can ignore. So any of those 6 negative ions that come from the strong acids or the 6 positive ions that come from the strong base, we can ignore those when they're in a salt. Now, what happens if we have a weak base and a weak acid? So the positive ion is not one of those 6 strong bases, and the negative ion is not one of those 6 strong acids. Then it gets really complicated because it depends on which one is stronger. So if the base is a little bit stronger than the acid, it'll be acidic. If the Ka, so we have to compare the Ka and the Kb. If the Ka of the cation is larger, it's acidic. If the Kb is larger, it's basic. Probably not going to give you any of those. Just makes it more complicated. But you should know what that means. All right, so now we get a little bit more complicated. So if you want to find out the pH of a salt solution, we already said this, we're going to need the Ka of the conjugate acid or the Kb of the conjugate base, depending on if it's acidic or basic. So for example, when we had that NaCN, we could ignore the Na, but we needed the Cn negative. Now the hydrolyzation gives us this. It's actually the opposite of this. We need the Kb for this. But if you looked on the table, you're not going to find a Kb for this. So they're not listed directly in the table book, but they are very easily related to the conjugate. So I'm going to show you how you can find it if you don't know it. So for example, since we need the Kb for Cn to do that problem, however, the only thing we could find is the Ka. So how are they related to each other? Well, this is going to be a lot of see if you can follow it. This is the reaction of HCN acting like an acid. Acid plus H2O gives us H3O plus and Cn negative. And the Ka value represents this equation, right? This is Cn negative acting like a base. Cn negative plus H2O gives us HCN plus OH negative. So this is the Kb expression. Now, remember, we sort of did this with delta H's, but then we also did this with K expression values. If we can find 2 equations that add together to give us a third equation, then the Ka values for the two equations multiplied to each other will give us the K value for the third equation. So let's add these two together and see what happens. The HCN cancels, the Cn negative cancels, and we have 2H2O plus 8 gives us H3O plus OH negative. Well, that's our self-ionization of water. And we know the K value with respect to that equation is the Kw. And so now we know how these three are related. The Ka times the Kb equals Kw. So Ka times Kb equals Kw. So as long as you know, if you're trying to find, now it does get complicated because do you need the Kb? Do you need the Ka? Well, if it's a salt, you're going to need the opposite one that you can than what you can find. So you're going to always have to find the other one. If you're just doing an acid or base, then you should be able to find the Ka for an acid or the Kb for a base. But if you're doing a salt, it's kind of the opposite, and so you're going to have to find the opposite one. So, like I said, we're not going to get into the complication where we need to worry about both ions hydrolyzing. We're only going to figure it out if one ion hydrolyzes. So we'll be able to ignore one of the two. So this is, we can figure out the pH of a salt solution in the same way that we found the pH of an acid solution or a base solution because these are weak acids and weak bases. The only difference, like I said, is that before you can do the problem, if it's a weak acid, you'll have to find the Ka given the Kb or find the Kb given the Ka. So let's do an example. All right, so what is the pH of a 0.1 molar NaCN solution? So again, how do I know this is a salt problem? Because I don't have an H plus. I have two ions that are neither H plus or OH negative. So it can't be an acid and it can't be a base because the two salts are neither H plus nor OH negative. So like I said, we could look up the Ka value for HCN, but we're not going to be able to use that in the problem because we're not dealing with HCN, we're dealing with Cn negative. So the first thing you want to do when you get a salt solution is you want to go ahead and analyze the two ions. We know that we can ignore the sodium because it comes from one of those 6 strong bases. So we're going to ignore the sodium and we're just going to be dealing with the Cn negative. The Cn negative is what's hanging around, so we're going to write the hydrolyzation of Cn negative in water. So here is that. So the Na, again, we can ignore because it's not going to do anything in water. But the Cn negative is going to act with water to give us HCN and OH negative. And as we said earlier, we can write the Kb expression for that. I don't know if it's going to come up or not, but this is just our normal base equation. So our Kb equals this. And now we could solve this problem without we know that it's 0.1 molar. And we can solve this problem as long as we know Kb. So the important thing to remember is that because we're not dealing with the acid, we're dealing with the salt, which is the base, we're going to have to use the Kb. It's going to give us OH negative, so we'll have to, but only Ka is given to us because that's all you can find in the table. So we're going to have to first find Kb. So Kb equals Kw divided by Ka, because remember Ka times Kb equals Kw. So divide by whichever one you know. Divide Kw by whichever one you know and you'll find the other one. So now there's our, so you remember this is a Ka, 4.9 times 10 to the minus 10th is a pretty weak acid, but it's a little bit of a stronger base. So because remember they're opposite each other. All right, so now we know the Kb, and now the rest we can solve very easily. So if we set up our ice chart, our CN negative is 0.1. We can set up our ice chart. We know that KB equals HCN times OH negative divided by CN negative, x squared over 0.1 minus x. We can do the same kind of evaluation, the CB over KB if it's greater. Okay, so didn't do all the math here for you, but we are able to ignore x compared to the 0.1 molar, so we can solve for x by taking the square root of both sides, and we get 1.4 times 10 to the minus 3, but don't forget that that's OH negative, and so we can find the POH. POH would be, what is that, 3.85, so subtract that from 14, and we get 11.15, which is definitely basic, greater than 7. So we would do the same thing if our positive ion was acidic. We would have to find the Ka from the Kb, and we could do the same problem. So it's really just the same problem. The only twist is you have to find the Kb first.